We'll be opening an automotive headrest and flattening with ExactFlat for Rhino. ExactFlat is capable of reading many different geometry types. For this video, we are going to import a step file that was originally created in SolidWorks. We will begin by clicking the Open button and selecting our headrest model, and then clicking the Open icon to open the model. We're going to accept the default options and just click OK. The first thing we notice about the model is that it's coming in upside down. If we rotate the perspective view around, we can see that the headrest is upside down. To correct this, we can use either the mirror command or the rotate command. So we will start by selecting the mesh. We're going to go to the transform toolbar, and we will use the rotate command to rotate this to the correct orientation. We will click an arbitrary spot for our center of rotation, and our first reference angle is going to be the horizontal x-axis. So we will hold shift on the keyboard to snap our second selection point to be on the horizontal x-axis. We will rotate our second reference angle 180 degrees, and again holding shift on the keyboard, we will snap our second point to the horizontal x-axis. Our object has now been rotated to the correct orientation. We will now proceed by maximizing the perspective viewport. We will do this by double-clicking the viewport title in the top corner here. Now our viewport has been maximized, giving us the greatest viewing area for working with our model. Our next step is we're just going to zoom to extents so we can see the most of our model as possible. Before we proceed, trying to work with this object in wireframe mode is a little difficult, and it doesn't give us a very good sense of the curvature of the object. So we're going to change our viewing mode from wireframe. We're going to right click on the viewport title to bring up our menu, and we're going to change our render mode from wireframe to shaded. This allows us to see the curvature of the model a little better. Now when this model came in, it came in as a single polysurface object. Although ExactFlat is perfectly capable of flattening polysurface and surface objects, it is preferable to flatten a mesh object, and this is because meshes give us the greatest degree of control and gives us access to our suite of pre-processing tools such as the adaptive and uniform remesher. As such, we're going to first create a mesh from this object. So we will begin by selecting the object. We'll go to our Mesh Tools toolbar, and we'll use the Mesh command to create a mesh. For simplicity's sake, we're going to use simple controls, and we're just going to create the most polygons possible. When done, we'll click the OK button, and soon we have a mesh. To keep the model document clean, we're going to separate all the different geometry onto different layers. So instead of just keeping our geometry in one layer, we're going to create a new layer. We'll do this by going to the Layers tab, and we're going to right-click in the white space and select New Layer. And we're going to give our layer a name of Mesh. Next, we're going to select our mesh, and using the Object Properties dialog, we're going to change the layer from Layer 1 to Mesh. We are also going to change the display color from white to by layer. That way the mesh inherits the color of the layer and not just a white mesh. Now we can make mesh layer the default layer by adding a check mark beside the layer name, and we can click the light bulb icon to turn off the polysurface layer. At this point, we have one single mesh representing all pieces. For this flattening job, we're going to create 4 different pattern pieces out of this mesh. So we will begin by first exploding the mesh. And to do this, we can use the Rhino explode command, or we can just type explode into the command line. So we will type in explode to explode this mesh. And it has exploded into 34 different meshes. From here, we can start to form logical pattern pieces by simply selecting them using the mouse. By holding shift, I can select multiple pieces, multiple meshes at the same time, and then we're just going to use the Rhino join command. So I will type join into the command line and press enter to join the meshes. We will repeat this process for all desired pieces. So I've selected all my faces, and now I'm going to type join into the command line, join them together. We will repeat the process for the back. By holding shift, I can select multiple meshes and then type join into the command line to join them together. For the last piece, instead of selecting all the faces, I'm going to select the 3 faces that I've already joined. Now I'm going to type invert into the command line to invert my selection. And now I can type in join to join these faces together. By joining these faces together, we have created a single mesh that is comprised of many different sub-meshes. If we were to flatten this with ExactFlat, ExactFlat would recognize the sub-meshes and it would explode them for us back into our component meshes. To prevent this from happening, we are going to use the Weld command to weld all the vertices together and basically reduce the coincident vertex count to 0. So we will start by selecting all our meshes, and we will type in weld into the command line to weld them together. We're going to use a weld tolerance of 180 degrees, and pressing enter finishes the command. Now we have 4 mesh objects that we will flatten with ExactFlat. Before we flatten with ExactFlat, we're going to use ExactFlat's mesh pre-processing tools to reduce the number of vertices of this mesh. As we look at the mesh, we can see we have a wide variety of triangle and quad sizes, ranging from fairly large. If we zoom in, we can see some very, very small triangles here. We can also see what are referred to as high aspect ratio triangles, and these are triangles that have very, very small angles at one end, mixed with very, very large angles at another vertex. Although ExactFlat can flatten these, they're not ideal for ExactFlat, and as such we have a couple different tools for pre-processing and conditioning these meshes, the most important of which is our adaptive remesher. So we will select all our meshes and we will click the adaptive remesher icon to start the adaptive remesher. The adaptive remesher will automatically compute reasonable tolerances for sewing tolerance, desired surface, boundary, and minimum edge length, as well as use the most appropriate options. So we're going to simply click the start button, and very soon we're going to start to see a new mesh created over top of the original. We're going to click yes to the high vertex count. We've got a high vertex count over 1,000 vertices, which is acceptable for ExactFlat when using the adaptive remesher. And very soon we're going to see a new mesh being created over top of the original. A couple of the characteristics of this mesh are that all the triangles are more or less equilateral, and when there is a change in size of triangle, the change in size occurs gradually over a large distance. We can also see that the edge tessellation has been preserved, so as we look at seams we can see that both sides of the seam share the same tessellation, and that is there's a single set of vertices along the edge that both right and left hand side share. All of these characteristics of the mesh make this a very suitable mesh for ExactFlat to flatten. After we've finished remeshing, we will change over to the ExactFlat toolbar and we will start to flatten these using the flatten command. We'll simply rectangle select all the meshes and press enter on the keyboard to accept the selection. And very quickly we can see our flat pattern. For our next step, we're going to minimize the perspective viewport by clicking on the perspective title, and we are going to maximize our top viewport by double clicking on the top viewport title. We're going to switch from wireframe mode by right clicking on the top viewport title and selecting shaded. And now, after flattening, we have 2 new layers created. One is the ExactFlat model layer and the other is the ExactFlat pattern layer. We are going to make the pattern layer our active layer, and we are going to turn off the model and the mesh layer. It's important to note that ExactFlat is a 2-stage flattener, and that means that ExactFlat does its flattening in 2 steps. The first step is what we are looking at now, and these are flattened using what are called pre-flatteners. So our pre-flatteners are a collection of different mesh flatteners that are very, very quick, but they produce meshes that are not optimized. In the case of this one, we have quite a bit of strain around the perimeter. For this piece here, we have quite a bit of strain, and the mesh is folded in on itself. This is the result of a projection flattening, and we have very similar results for the remaining meshes as well. ExactFlat has a number of pre-flatteners, including our fracture pre-flattener, we have our pelt pre-flattener, and we have a collection of convex combination map pre-flatteners, as well as a number of pre-flatteners that are not actually featured in our toolbar yet. If we select the fracture pre-flattener, we can select any edge on a mesh to act as a starting point for a new fracture. We can see the results of this fracture have both reduced the strain on the surface as well as expanded the pattern perimeter and eliminated a lot of the strain on this piece. When used on the second piece here, we can see that we've eliminated the vast majority of the strain. However, if we look at the corner over here, we can see a cross highlight, which indicates the presence of flipped triangles or folds or wrinkles in the pattern. We'll use the fracture command on the remaining pieces, and our primary goal here is to eliminate a lot of the excess strain that's in the pattern. We can try the pelt command on some of the pieces, and we can see that we end up with a slightly different starting pattern, although it is still unoptimized. In the case of this piece, we get this better starting position without flipped triangles, but this starting point has more strain in it. The important thing to understand is that any of the pre-flatteners can be used at any point in time, and you can use them as many times as you want. This is just a result of the first stage flattening, and the second stage is always going to be optimized, and the optimizer is what's going to give us our final flat pattern. The goals of using the pre-flatteners are to achieve a decent starting point for the optimizer that has minimal strain, such as this piece, and no flipped triangles. In the case of this piece, we can't optimize this piece yet because it has a flipped triangle. The best way to correct flipped triangles are to either try a different pre-flattener, or in the case of fracture, we can try fracturing from different starting locations, and depending on the starting location, we end up with a different initial flat pattern that may or may not have flipped triangles. We can also try using ExactFlat's automated flip triangle removal process to remove the flipped triangles for us. And in this case, the process was successful and we no longer have any flip triangles on this pattern piece. It may be beneficial to turn off the ExactFlat edge highlight, and this will remove the triangulated mesh from the pattern piece, and we may also turn off the strain analysis. In the case of rendered textured objects, turning off the strain analysis will also allow us to see the texture of the object when in rendered mode. If the strain analysis is turned on, even if we are in rendered mode, we will only see the strain highlight. We will turn our strain highlight and edge highlight back on and go back to the tools toolbar. Once we have a decent starting point for our flat patterns, we will use the ExactFlat optimizer to reduce strain and sag to as close to zero as possible. For this demo, we're going to use a simple cotton model, and we're going to turn pre-process on to reduce our optimization time. Very quickly, the optimizer starts minimizing strain and sag and optimizing the pattern piece. As the optimizer runs, we can see the shape is changing to better, so the pattern piece better fits over top of the original 3D model. You can also see the strain highlight changing, indicating the strain throughout the pattern piece is changing. For most pattern pieces, this shift is going to be from red and green colors down towards white and cyan. As with most parts of ExactFlat, the strain legend is very configurable through the ExactFlat options panel. By default, the strain analysis is configured so white represents 0% strain, cyan is about 5% strain, green is 10% strain, yellow is 15%, and red is 20% or more. If at any point in time the optimizer reaches a point where the pattern is good enough and you just want to continue, we can click either the skip button to skip the current piece, or we can click the stop button to stop optimizing altogether. In this case, we click the skip button to skip optimizing this piece so we can proceed on to the next pieces. After the optimization is complete, we can click the OK button to close the spring status dialog. And now we are ready to do our patterning of these pattern pieces. To begin, we're going to rotate this pattern piece so the bottom edge is perfectly horizontal. And to do this, we will again use the Rhino rotate command. So we'll click the rotate icon in the toolbar. We're going to select the bottom edge as our starting reference point. We will select our the other corner as our first reference point, and just holding the Shift key on the keyboard, we're going to snap this to the horizontal x-axis. We are now going to use the ExactFlat Find command by clicking the binoculars icon in the ExactFlat Tools toolbar, and we're going to set a find offset of about 20 millimeters. Now, as we click on edges, as we highlight over one of the edges, we can see the neighboring edges also being highlighted on the piece to the right. And when we click on an edge, we're going to see that our neighboring piece is automatically translated and rotated to match the orientation of the selected edge. Using this tool, we can very quickly rearrange the pattern pieces so they are much easier to work with in ExactFlat. This allows us to easily place notches on our pattern pieces, as well as identify any meshing or flattening errors that have occurred. Our next step is to add notches to this the pattern, and notches are a combination of a text tag as well as either a slit notch or a V-notch. Notches can be configured. We can change the color of the notch, and we can change the type of the notch between I and V notch, and we can also manually adjust the width and length of the notch. When the length is set to 0, the length is going to automatically be the length of the seam allowance added to our pattern piece. If we manually specify the length, then the length is always going to be however many the length entered in the unit system that the document is currently used. In this case, we're going to specify our slit notch to be 5 millimeters in length. We'll click the Add button to start adding notches to this part. As I select edges on the pattern piece, we can see that the notches are showing up on the neighboring pattern piece as well. We can also add notches to the reference model by simply switching back to our model layer. So we'll make the model layer the active layer. We'll hide the pattern. We're going to minimize the top viewport by double clicking on the top label. We'll maximize the perspective viewport by double clicking on perspective. And now we can rotate our model around, and we can start adding notches to the 3D model. We will again open up our notch tag dialog, and we'll click Add to start adding notches again. So as we select our edges, we can see that our notches are showing up where we select. And if we were to view our pattern again, we would see that the notches are being added to the pattern as well as the 3D model. The 3D reference model always represents the exact same changes made to the pattern and vice versa. So any change made to the model will be represented in the pattern, and any change made to the pattern will also show up on the 3D reference model. Once all our notches have been added, we are ready to start creating a DXF. To do this, we will click the DXF icon in the ExactFlat Tools toolbar, and we will specify a DXF name. We can use the import command to import the DXF back into the current document so we can have a look at the structure of the DXF. As we zoom in, we can see that all the notches have been created where we specified them. We can also see that each notch has a tag added to it. And when we start looking at the structure of the pattern, we can see we have a blue seam line, which represents the perimeter of the pattern piece, as well as a red cut line, which is the pattern piece plus an optional seam allowance. The optional seam allowance is configured in the ExactFlat Options panel. And if we move this pattern piece over top of the original mesh, we can see that the blue seam line matches the perimeter of the mesh. Furthermore, if we start looking at the layer structure, we can see that all the cut lines have been created on a cut layer, and we can turn that layer on and off. All the seam lines have been created on a separate seam layer. All the notches have been created on a separate notch layer, and the tags themselves have been created on a separate tag layer. So if we zoom in and turn the tag layer off, we can see the text disappearing. This is important because when we bring this over to a cutting table, we can change the layer names, and we can also turn individual layers on and off, and this allows us to very easily assign different tools, whether it's a cutting tool or a pen tool, to the different layers. So this has been a very quick overview of the basic functionality of ExactFlat for Rhino. I hope this video has been helpful, and have a wonderful day.